All right, here we are, section 5.2, evaluate and graph polynomial functions. So what is a polynomial? It's a monomial or a sum of monomials. And what is a polynomial function? So the equation here written quite elaborate. Basically, you can look at it and say, it's x raised to some power. It could be x raised to the power 5. There's a coefficient in front of the x term, and that number has to be always a real number. So it could be like 2x to the power 5 plus 2x to the power 4, and so on. All the exponents must be whole numbers. So powers of 2 and 3 and 4 and 5. We can't do powers of like 4.5. Synthetic substitution. This is a different way of substituting into a polynomial function other than direct substitution. But you hold off on thinking about that for a second until we get to our example. And then end behavior. And this is probably the most important part of this section. Oop, that was supposed to be a star. Not bad. End behavior of the polynomial function. As x approaches a very large number, positive infinity, or a very negative number, what does the function do? So first of all, let's look at these two examples. So example A, is this a polynomial function? And the answer is no, and it is because of this power. We can't have powers of 2.5. It must be a whole number. So whole numbers are like 3 or 2, but 2.5 is not a whole number. If we look at example B, is this a polynomial function? And it certainly is, right? We have power 2, power 1, and power 4. All the coefficients are real numbers, and this therefore is a polynomial function. If we rewrote it in the order of the highest exponent and down, that's typically how we like to present our polynomial functions, and we call that standard form for a polynomial function. Then we say the highest exponent is the degree of this polynomial. This is a degree 4, a quartic. Degree 4 or degree 5, this naming isn't always as important. And the leading coefficient is 9. Again, the coefficient, the number that goes in front of the highest powered exponent is called the leading coefficient. It has a lot to do with the end behavior. It's a very important number, especially whether or not it's positive or negative. Hey, why don't you take a look here at this polynomial, or excuse me, at this example, and tell us if it is, well, I guess it's not asking, it is a polynomial. Sorry, I should read the directions more carefully. Can you state the degree, the type, and the leading coefficient for the function? Here come the answers. So we say it's the degree 4. We call it, again, the type is quartic. Again, don't be nervous about this. I really never ask you that. I do want you to be able to see that it's, oops, that was supposed to be an arrow. Degree 4. I didn't mean to cross off the 4. Again, the order was not, this was not presented in standard form, so you have to go look around and say, oh, that's the highest power. So the leading coefficient here would be -3, and make sure you caught that negative. Well done. So here we go, beautiful synthetic substitution. And it's a really neat technique, and you definitely want to know how to do this, and we'll practice this quite a bit in the classroom. So first of all, we need to make sure that this polynomial is in standard form, and notice it is, right? Power 4, power 3, power 2, skip power 1. That's interesting. And then we have the coefficient 3. So realize what we're trying to do is plug 2 into this equation. And you should say, hey, that's, I can do that with a calculator. So I showed you down here, right? We would plug 2 in for x, hit enter, and the answer would be 35. So check out this little technique. Right? So if you want to fill in your note sheet, this would be descending. Right? Bring down the leading coefficient, multiply the leading coefficient by 2, and then add. I'm going to show you this, but I'm sure some of you want to fill this out as the book would have liked. Let's just get into the problem. So notice how we set up these coefficients. So I took the 2 in front of the x power 4, then the 3 in front of the x power 3. The -6, and then this is a big deal, right? There's a plus 0 x to the power 1. It's not written here, but that is a big time placeholder, big time. If you miss this, the whole problem goes wrong. So it's very important that you catch that piece. Then, because we're plugging in 2, we put a 2 here. And then we have this nice, L bracket. So watch, here's the system. We drop the 2. We now multiply this 2 by this 2. And get 4. We add the 4 and the 3 and get 7. We multiply again by 2, why 2? Because it says so right here, and get 14. Add these guys up, we get 8. 8 times 2 is 16. Now you should feel this is repeated. We keep multiplying by 2, multiply by 2, multiply by 2. We add, we add, we add. We're going to add by 16. Yes, we're going to multiply by 2 again. And then we add those guys up and we get 35. And you should say, whoa, check that out. That's the same 35. Granted, this probably came about when graphing calculators weren't around, and if you didn't have a calculator, you could see that this is a nice system. So this is called synthetic substitution, and we will practice this in class. End behavior. Wow, this is quite a busy little slide for you. I'm going to try to sum this up and give you another slide on the next page. But basically, we're saying, look, if the leading coefficient is positive, then as the function gets more, goes in the negative x direction, the function also goes in the negative y direction. So you could kind of think of f of x maybe as y. And as x gets very, very large, the y values get very, very large. If your leading coefficient, and that is negative, and you're dealing with odd polynomials, as x gets very small, the function actually gets very big, the y values. And as the x values get very large, the y values get very, very small. Now, both of these cases were for odd power. So this would have been, for these two, would have been x to the power 3, or x to the power 5, or x to the power 7. All highest exponents would be odd powers. For even, so something like x to the power 4 or x to the power 6, the way this works is x gets very large, the function y values gets very large, and as x gets very small, I think I said larger, as x gets very small, the function gets very big, and as x gets very big, the function still gets big. And then if the leading coefficient is negative, then it's the opposite. As x gets very small, the function gets very small. As x gets very large, the function still gets small. This is a pretty confusing slide. Let me see if I can't help you by kind of giving you a picture sense. So odd-powered polynomials, x to the power 3, x to the power 5. If the leading coefficient is positive, then the function's going to end up looking something like this. And so what does this mean? Well, as x gets large, right, so maybe we'll put this on the xy axis. As x gets very large, the function goes up to infinity. As x gets very small, the function goes down to infinity. If the leading coefficient is negative, then we flip this and we basically go in the opposite direction. It looks something like this. As x gets very, very large, right, as x gets larger, the function goes very, very small, negative. And as the function x values get smaller, the function actually goes off to infinity. So those are odd-powered. Even-powered functions like x to the power 2, x to the power 4, x to the power 6, right, and so on. If your leading coefficient, right, is positive, like an x to the power 4, we have something that looks kind of like this, where the ends both go to infinity. So even as x gets big, the function gets big, but even if x gets very small, the function still goes up to infinity. And for odd leading coefficients, you can see that it would be the reverse of that. So I'm just kind of making up, but if you have a even-powered polynomial function and the leading coefficient is negative, for example, like negative 2, x to the power 6, leading coefficient is negative, the end behavior, both as x gets very big or very small, the function goes to negative infinity. This would be a nice page to have in your notes. So how do we graph a polynomial function? So here we go. This is a third-order polynomial function. The leading coefficient is negative. So just from that information, you know that the shape of this, the end behavior, should look something like this. Right? And that is so important that you get that piece. The negative would cause this guy to flip, right? If that had been positive, if you go back to the last slide, right, if it had been positive, it would look like this end behavior. But because that leading coefficient is negative, it looks like this end behavior, right? And if this had been a power 4 with a negative, we would have looked at something like this, where both are going down. That's a great way to start this start graphing this polynomial function. So first we need a table of values, right? And so I'm skipping a lot of effort here. You could do synthetic substitution. When you plug -3 in, you get 38. And again, if you're like, how did he know that? Well, you'd plug it in, and I'm skipping that just for the sake of time. We would plug in -2, we would plug, so it kind of takes quite a while. This is easy, right? 0 you can see is just -1. Plug 1 in, get 2, 3, and -4. So you now plot these points, right? So first of all, -3, I can't even get it on the graph. I can't get -2 on the graph, but I know they're way up here. At -1, I'm at 0. At 0, I'm at -1. At 1, I'm back up here at 2. At 2, I'm up here at 3. And then at 3, I'm down at -4. Okay, I believe I'm recording again, having some software issues. The whole software melted down on me, so I think I'm back and I am recording. Apologize, I can maybe edit this out for you. So I believe we are still trying to graph this polynomial function. It's a third order. I'm at home now too. It was a little crazy. And leading coefficient's negative. So again, we know from the behavior of functions that it should look like something like this. Plotted, I plug these points in using synthetic substitution. I can also show you on the calculator how to do this in a table, which is a nice feature on your calculator. And in the end, I have these, it looks like I've plotted, or I've calculated 7 points. These first two guys are way off the scale, but again, they're way up here. And by looking at this guy, I should be able to connect these dots. And so here we go. I'm going to do the best I can. Looks like I'm coming down. I'm going to go back up. Somewhere here I got to turn, and then I need to bring this guy back here. And so this is, this is a pretty decent sketch. You should be saying, well, how far down was this supposed to go? And that's pretty interesting. This minimum here, this is called a relative or local minimum. To find that's very hard algebraically, and somewhere, probably if I really want to make this even better, I'd plug in -1/2. And then here as well, it looks like between here there's some turning, I may have gone up more like that. I don't know. And again, I maybe should have plugged in 1.5. So again, if the degree of the polynomial is odd, which it is, right? Why do we know it's odd? Because it's power 3. 3 is an odd number. And the leading coefficient is negative. And why is it negative? Because it's -1. Then as the function the function will I actually don't like the way this is written. As x goes to -infinity, or as it goes smaller and smaller, the function actually increases. This goes to infinity. And as the x values get very, very large, as x gets bigger this way, the function actually is constantly decreasing, so it goes to -infinity. And our last slide here is for you to try. So go ahead and see if you can't do synthetic substitution, calculate an answer, and then also can you try to graph this function. Again, it's a fourth order, odd. So if we go back to our table back here, it should look like this guy here, right? It's an even powered and the leading coefficient odd. So the end behavior, the two ends should go both down to -infinity. Oops, there's the answer. Go ahead and hit pause, and let me show you the answer in a second. Here's your answer. So for synthetic substitution, I can walk this through. You should have had -2. Then you make this nice bracket, right? We look carefully, and the coefficients here are -1, then 3, then 1, and then -4, then -1. And so the method here, again, we drop, and we just say this is -1. Then we start the multiplying. So -1 times -2 is +2. We add, we multiply, we add, we multiply, we add, we multiply, then we add. And that's how we substitute. Hopefully you got that. We need to practice this and definitely get it in your note sheet. Here's the graph. So hopefully you plugged in a bunch of points, right? We plugged -2 in, we got -29, so way down here, -1 was 0. And then hopefully you connected some smooth. Again, how high this goes up, we don't really know. And how low this goes, again, we don't know. And how high, but we should have this general shape. Okay, thanks so much for watching, and see